Molecular structure and VSEPR theory is part of the Flipped Learning in General Chemistry series. This video will teach you to predict the geometry of a molecule from its Lewis structure using valence shell electron pair repulsion. After completing the assigned problems, you should be able to identify electron pair geometries and molecular structures and create three-dimensional drawings from Lewis structures. Valence shell electron pair repulsion is a model that assumes the best geometry for a molecule is the one that keeps the valence electron pairs as far apart as possible. The central N atom in ammonia has 4 valence pairs, 3 bonds, and 1 lone pair. The lowest energy structure of ammonia minimizes the repulsion between these valence pairs by adopting a tetrahedral geometry. This is called the electron pair geometry of the molecule. Notice our drawing convention. A normal bond is in the plane of the screen. A wedge bond is coming towards you, and a dash bond is going away. This is how we'll show three-dimensional structures in a two-dimensional drawing. The bond angles in a tetrahedron are all 109.5 degrees, which gives the greatest possible distance between 4 objects arranged around a central point. There are 5 electron pair geometries that we'll consider here. 2 electron pairs around the central atom prefers a linear arrangement with the pairs 180 degrees apart. 3 pairs are arranged in a trigonal planar geometry 120 degrees apart. We already saw the tetrahedron, which has an ideal bond angle of 109.5. Molecules with 5 electron pairs adopt a trigonal bipyramidal shape, which is a unique geometry in this group because there are 2 different positions. The 3 atoms in the middle are called equatorial, and they're all 120 degrees apart from each other. The top and bottom positions are called axial, and they're 90 degrees from the equatorial positions. The final shape is an octahedron with 6 pairs around the central atom. It might look like there are axial and equatorial positions here as well, but there aren't. All groups in an octahedron are the same, and they're all 90 degrees apart. Notice 2 things on this slide before we move on. First is how the standard line-wedge notation is used to show all of the three-dimensional shapes on this slide. And second is the trend in bond angles, which is decreasing as the central atom gets more crowded. Now we need to define the molecular structure of a molecule and contrast it with the electron pair geometry. Here are 3 examples: methane, ammonia, and water. They all have the same tetrahedral electron pair geometry, but they have different numbers of bonds to the central atom. The molecular structure is the shape of the molecule considering only the atoms. If we redraw these examples with the dash wedge convention and omit the lone pairs, it's clear that we have 3 different shapes. Methane has 4 bonded atoms, and its molecular structure is also called tetrahedral. Ammonia has 3 bonded atoms, and this shape is called trigonal pyramidal. Finally, the water molecule with 2 bonds is described as bent. Next, we'll go through all 5 electron pair geometries and see what molecular structures are possible. For 2 electron pairs, our only choice is a linear molecular structure with a bond angle of 180 degrees. The trigonal planar electron pair geometry has 2 possible molecular structures: trigonal planar with no lone pairs, and bent, which is also known as angular, with 1 lone pair. Each structure has an idealized bond angle of 120 degrees. We've already seen the 3 possibilities for a tetrahedral electron pair geometry. Notice that the name bent is reused here, but the bond angle is different from the bent structure that was on the previous slide. The trigonal bipyramidal geometry has 4 possible structures: trigonal bipyramidal, sawhorse, which is also known as seesaw, T-shaped, and linear. Because the trigonal bipyramid has 2 different positions, axial and equatorial, we have a choice as to where to put the lone pairs. The VSEPR model assumes that the lone pairs occupy more space than bonding pairs, so we put them in the less crowded equatorial positions. We'll talk more about this when we consider real versus idealized molecular structures. Finally, we have an octahedron, which can be octahedral, square pyramidal, square planar, T-shaped, or linear, depending on the number of lone pairs. Although all the positions in an octahedron are the same, when there are multiple lone pairs, they're placed to stay as far apart as possible. This is why, for example, the square planar shape has two lone pairs that are on the opposite side of the molecule from each other. Now it's time for you to practice on your own. Pause the video and determine the electron pair geometry and the molecular structure of the sulfite ion. Practice drawing the 3D structure using the dash wedge convention. I've intentionally given you a structure that has a double bond. How do you think this is handled in the electron pair geometry? The two pairs of electrons in the double bond can't be separated from one another because they're both connected to the same two atoms, so the double bond is only counted once. That means the electron pair geometry for sulfite is tetrahedral. There are 3 atoms attached to sulfur, so the molecular structure is trigonal pyramidal, and it's drawn like this using dashes and wedges. Don't forget to complete the problem set and read the textbook sections assigned with this video. You should come to class prepared to identify electron pair geometries and molecular structures from Lewis structures. Thanks for watching.